Hello, Mr. Dato here. Just wanted to make a quick video for you since I was unable to be present today. What we will do today is take a brief set of notes and we will review what we have learned up to this point. And just a quick reminder that we will have a test this Friday that will go over everything that we would cover before today and today. Now, if there's any point where you're having a hard time understanding anything at all, I'll be there next class period and we will review the material and go over it a second time. But I just wanted to make sure that we got the material in so that you guys can be prepared for the last exam of the year. So go ahead and open up your books to page 78 and I will give you a moment to do that. And then we will start reviewing some of what we've learned up to this point because we will go over it. We'll use some of this information today. So go ahead and open it to page 78. Now, the first thing I want to do is I want to talk about what we've learned up to this point, and what we've learned, part of what we've learned up to this point is this equation right here, which is Q equals mc delta T. And just a brief reminder, Q is heat energy that is absorbed or released from either a chemical reaction or a substance gaining or losing heat energy, thermal energy, which affects its temperature. So again, Q is heat. Now M is mass, we all know what M is. C is specific heat, and delta T, which is this triangle right here, it means change in temperature, which is the final temperature. Again, it's the final temperature minus the initial temperature. So don't forget to do the final minus the initial. Sometimes you will have a negative change in temperature. So up to this point, that's what we've learned. Another thing that we've learned is we've learned if we have a system that we can have energy exiting the system. And so when we have energy exiting the system, this is called an exothermic reaction. Another type of thing we can have is where we have heat going into the system, and this is an endothermic reaction. So if heat is exiting a system, it's an exothermic reaction. If heat is going into a system, it's an endothermic reaction. An example of this would be a liquid. Let's go ahead and do that. A liquid going into a solid. And so for a liquid to go to a solid, you have to decrease the temperature. And to decrease the temperature, heat has to exit the system. An example of an endothermic reaction would be, let's go ahead and change up the temperature here, or the color, would be a liquid going to a gas. And so this would be an example of endothermic reaction because the substance had to absorb energy to go from a liquid to a gas because it had to increase its temperature, which means it had to absorb energy. So those are, this is kind of a brief overview of what we've learned so far. We'll go over it more next class period when we do the review, but just wanted to touch on those things because it will be important for what we're going to learn today. Okay, so let's go ahead and talk about what we're going to learn today. All right, so make sure you're open on page 78. Make sure you have a writing utensil to write things down. And so what we're going to start talking about, we're going to start talking about enthalpy change. And so what enthalpy really is, it is the amount of energy that is within a substance. So all matter has a certain level of energy associated with it, and what we're going to talk about is chemical potential energy. For example, gasoline has quite a bit of chemical potential energy associated with it. whereas maybe carbon dioxide does not. So we use gasoline to power our cars and we get energy from it. So that is going to have quite a bit of enthalpy or chemical potential energy associated with it. So we're going to talk about that. And so what we're going to talk about is enthalpy change. It's going to be the change in energy. And so the first thing we're going to talk about is we are going to talk about change in enthalpy, which is the amount of energy that is absorbed or released as heat by a system when the pressure is constant. Okay, so don't worry about too much of the pressure is constant for a moment, but just worry about it's the specifically it's the amount of heat. It's the amount of heat that is given off or absorbed by a certain process. All right, so let's go ahead and talk about some examples of enthalpy change. And so let's consider an endothermic reaction. Now again, what does endothermic mean? It means that energy is being absorbed. So let's imagine that we had some reactants, and the reactants have a certain amount of potential energy. And again, this is considered chemical potential energy. And so we're going to call these reactants. So we'll put an R right here. Go ahead and write this also on your notebook so that you can kind of follow along with it. All right. Now, as the reactants turn to products, they're going to absorb energy. And so what happens is the products are going to end up with more energy than the reactants. So to go from reactants to products, they need to absorb energy. And so as you can see here, the reactants are a lower energy than the products. So because they absorb energy. So let's go ahead and complete this picture. We'll talk about this, the rest of this later, but the way the picture works actually is there's also a little hump here like that. So we'll talk about that later. But as you can see, the reactants go absorb energy as they turn into products. Now let's go ahead and talk about an exothermic reaction. Again, that's where heat is exiting, and so what we're going to do is we are going to have reactants they have a certain amount of potential energy. Again, this is chemical potential energy, and as they go from reactants, it's an R there, when they go from reactants to products, they will actually lower their potential energy. And the reason why the energy is going down like this is because it's releasing energy. Energy is leaving the system. It's going out as heat to the surroundings. And again, heat is being released by the system to the surroundings, and that is what is being given off there. All right, so let's go ahead and complete this picture. Also, it's going to be the same sort of thing as the other picture with, do this, all right, where we have the hump like that. And we'll talk about this hump here in a moment. We'll come back to this. So go ahead and take a moment to copy those down, and we will move on. All right, so okay, so what we're going to now do is talk about endothermic and exothermic reactions, and this is going to be very similar to what we were talking about before with endothermic and exothermic processes, such as liquid turning into gas and absorbing heat, which is endothermic. So, but now we're talking about chemical reactions. So, in an endothermic reaction, energy is released. All right, just like what we talked about before, energy is released. Okay, so now let's go ahead and talk about how this relates to endothermic and exothermic reactions. All right, so we kind of already briefly talked about this, and so endothermic reactions are reactions where energy is going to be absorbed. All right, so energy is absorbed, that. And if you remember from 2 class periods ago, we learned that in a endothermic reaction, that Q is going to be positive. And the reason why it's positive is because it's absorbing energy. So you have a positive heat energy going into the system. And we're going to call delta H positive as well. Now again, what delta H is, that is the enthalpy change. Q and delta H, for this class, we're going to consider them the same thing. That the heat energy is going to be the same as the change in energy for the system. All right, so again, this is what delta H stands for. It stands for the enthalpy change of the system, which means that it's the change in energy. It's the heat that's given off. So now, a type of endothermic reaction is where we break bonds. Okay, so we're going to have broken bonds. When we break bonds, that is a endothermic reaction. It actually requires energy to break. So breaking bonds. So breaking bonds is an endothermic reaction. Now, to go ahead and kind of talk about how we can think about this, if we have some gasoline, does gasoline instantly react with oxygen in the air if it's just sitting there? Of course it doesn't. What do you need to do to get gasoline to start reacting, to start burning? You need to put a flame to it. You need to heat it up and add energy into it to get it to start. And the reason why that is because you're breaking bonds, all right? It's because you're breaking these bonds. It takes energy to break bonds. It's kind of like 2 magnets. If you were to take 2 magnets apart, you have to put energy into breaking those magnets apart. Okay. Now, energy, if a reaction requires energy to start, energy appears in the reactant side of the chemical reaction. All right, so let's go ahead and put that in there. We're going to put the reactants in there. Okay, so let's go ahead and talk about when we're writing a chemical reaction, where do we write energy? So we can actually incorporate energy within a chemical reaction to show if it's endothermic or exothermic. And when we do that, we will put energy in the reactant side of the chemical reaction. So we will put it in the reactant side of the chemical reaction, because if something requires energy, if a reaction is endothermic, it requires energy to proceed forward. It needs to absorb energy, so that's going to be a reactant. So let's go ahead and take a look down here. We can see this right here. This chemical reaction is actually an example of an endothermic reaction. And the delta H is positive, just like it was up here. You can see delta H is positive for endothermic reactions, and Q is positive as well, which is the same thing. And so this right here tells us that it is a endothermic reaction. So what we do is we take this reaction right here, and we need to add this to the reaction. And so because it's positive, we have to add it to the reactants side. And so let's go ahead and add it to the reactant side. So we're going to add 92. We're going to add 92 to this side. And what we end up with is this. All right, so it looks just like that. This is an endothermic reaction. Okay, so let's go ahead and talk about exothermic reactions. Exothermic reactions are obviously the opposite of endothermic reactions, and so energy is released. And when energy is released, we have a negative delta H, a negative Q, and a type of exothermic reaction is actually bonds forming. So when you form bonds, this is an exothermic reaction because when two atoms come together to form a bond, they release energy because it is favorable for them to form bonds. All right. So again, breaking bonds is an endothermic process, and then when new bonds are formed, that's when energy is released. And energy appears in the product side. They appear in the product side of the chemical reaction. So let's go ahead and uh, do the same example. So here we have an example of an exothermic reaction. Now, how do we know this is exothermic? Well, if you take a look here, this is a negative delta H. Again, endothermic processes are positive, exothermic processes are negative. And so because it is negative, we add it to the product side. And so what we end up getting is we end up getting this reaction plus 324. Now that might be a little confusing because why is it plus 324? Why is it not negative? Why don't we subtract 324? Well, the reason why this is positive is because if you were to think about, for example, a gasoline burning, one of the products of gasoline burning is heat. So heat is produced. So if you take a look, energy is being produced. Now, this energy is given off to the surroundings. It's still there, but it's not being added to the system. So don't let that confuse you. When we put this inside of a chemical reaction, we always make it positive. Okay, so now let's talk about how we can actually calculate the enthalpy change of a reaction. So the enthalpy change of the reaction is represented by this crazy looking formula right here. So let's go ahead and talk about this a little bit. And if you take a look, we have this formula that has these kind of funky looking letters in here. And so let's go ahead and break it down a little bit. What this triangle means, again, it means change in enthalpy. So this is the change in energy of the substances. And so what this right here means, this means the sum of. Again, what it means the sum of the heats of formation. Alright, and we will talk about this in just a moment, but it is the sum of the heats of formations of the products. Again, if you take a look, that's where this is right here, minus the sum, this right here, the sum of the heats of formation of the reactants. And so again, it's the sum of the heats of formation of the reactants. And so let's go ahead and talk about what that really means. Well, first of all, what is heats of formation? Let's talk about what heats of formation is. And what heats of formation is, heats of formation represent the amount of heat that is given off or absorbed when a substance is formed from its elements. And so in a thermochemical equation, if you take a look here, it's a chemical equation that includes the enthalpy change of that reaction. And so let's go ahead and talk about that a little bit here. The coefficients represent the number of moles. Now, what this right here is, this is one variable, and you can see this right here is actually right here as well. So this is what this and this here are the same thing. So what the heat of formation is, it tells us, again, how much energy was absorbed or gained to make 1 mole of that compound. For example, liquid water, to make liquid water, we can make it from hydrogen gas and oxygen gas. And when we make 1 mole of that substance, when we take hydrogen gas and react with oxygen gas, which both of those are elements, when we react them together to make water, it will produce this much energy. When water is formed, when it is, again, heats of formation, when water is formed, it releases this much energy. And again, it's being released because of this negative there. And so what happens is we actually take elements and we define the elements. We say that they have a delta H of 0. So they have a heat of formation of 0 because, again, what we're talking about compounds. It's the amount of heat gained or released when 1 mole of a compound is formed. So what you want to take from that, from above, we're on the next page now, what you want to take from above here, all that matters is that to calculate the delta H of the reaction, we have to take the sum of the heats of formation of the products, and we minus the sum of the heats of formation of the reactants. Now the good thing is you will always be given the heats of formation. So let's go ahead and take a look here at this chart. So go ahead and take a look at this chart, and these are all heats of formation. And so you'll be given the heats of formation. So for a chemical reaction, all we have to do is take the sum of the heats of formation of the products, we add them all together, and then we subtract the heats of formation of the reactants. So let's go ahead and do a practice problem right here. We're going to do reaction 1 here. And we are going to take the sum of the heats of formation of the products. These are products right here. And we're going to subtract the sum of the heats of formation of the reactants. So let's go ahead and take a look here. Now zinc, if you take a look, zinc is an element. And let's go ahead and look back at our notes here. Elements in their natural states will have a delta H of formation of 0. And so the heat of formation for an element is 0. So if we were to do this, all we need to do is we take the heat of formation for zinc, which is 0, and we add the heats of formation of the hydrochloric acid here, the HCl. Well, what is the heat of formation for HCl? Let's go ahead and take a look at our chart up here. Here is HCl, and the heat of formation for HCl is this. All right, so we have to add negative 167.16. Now, one thing I want to point out here is hydrochloric acid in this chemical reaction has a coefficient of 2. So we actually have to multiply this by 2 because there's 2 hydrochloric acids. And so if you take a look, this actually satisfies this part of the reaction. Again, we take the sum of the heats of formation of the products, and these are the products. Okay. All right. Now what we do is we subtract. Now we need to subtract the sum of the heats of formation of the reactants. And if you take a look here, these are the reactants. So again, it's products minus reactants. So let's go ahead and take a look here. So let's take a look at hydrogen gas here. Well, what is the heat of formation for hydrogen gas? Well, it's not on this chart. Why is it not on this chart? Well, if we take a look up at our notes, again, elements, what do elements have? They have 0. And so let's go ahead and put 0 in there. So it's we have hydrogen gas plus we have the heat of formation for zinc chloride. So let's go ahead and take a look at zinc chloride up here. Here is zinc chloride. Here's the heat of formation for that. And so we get to add that in there as well. And so again, I like to put it in parentheses just because it's a negative value there. And so it's going to be a negative 415. And now all we need to do is type that into a computer. And so let's go ahead and recap real quick what we did. All right, so there we go. Let's go ahead and recap real quick what we did. We took the sum of the heats of formation for the products, which are these right here, which is represented by this right here. And we subtracted the sums of the heats of formation for the reactants, which are here, which we put here. So we added them up, and then we subtracted the ones that are all the reactants added up together as well. So let's go ahead and actually do that. Let's type that into a calculator here, and so we can see how to do this. So what we're going to do is we're going to do parentheses. We have to turn it on first. Parentheses 0 plus 2 times negative 167.16, and then we're going to do parentheses closed, and then we're going to subtract parentheses 0 plus negative 415.1, parentheses closed, and what we end up getting is we end up getting 80.78. Alright, so in this first problem here, we get a delta H, we get a change in enthalpy for the reaction of negative 80.78, and the units for that is going to be kilojoules. Kilojoules of energy. Alright, so let's talk about number 2. Now we're going to predict whether the reaction is endothermic or exothermic, and whether it heat is released or absorbed. So let's go and take a look at this. Now, is this going to be endothermic or exothermic? Well, is it positive or is it negative? And if you take a look here, it's positive, and if we go all the way back up here at our notes, let's go back up here, if we have a positive delta H, it's endothermic. And so what that means is that this reaction is going to be an endothermic reaction. So let's go ahead and answer that question, endothermic reaction. And that is the answer for number 2. Now number 3, if we take a look up here, number 3, we need to write the thermochemical equation with the energy values involved. And so what we're going to do is we're going to rewrite this equation right here, and I get to just copy and paste it down here, but you get to write it. There we go. And we need to add this energy in there. Now, if it is endothermic, do we add it in the reactant side or do we add it in the product side? We add it in the reactant side because since it's endothermic, it's going to absorb that energy and it will require that to be in the reactant. So we'll go ahead and put that there. And so that is how you do number 1. Okay, so let's go ahead and do number 2 now. Reaction number 2, and I'm going to go through this a little bit more quickly just for the sake of time, and so we'll go ahead and do this, and then I'll have you guys do some practice problems, and that's what you'll do for the rest of the class. Well, not for the rest of the class, but you'll do it some practice problems, and then yeah. So let's go ahead and do that. Alright, let's go ahead and take a look at reaction 2 now, and what we're going to do is I'm going to go ahead and do this a little bit more quickly, just so that you guys can go ahead and get some of the practice problems done, and then we'll take it from there. So let's go ahead and take a look at this here. Now again, it's the sum. It's the sum of the products right here minus the sum of the reactants right here. And if you take a look, these are the products right there, and these are the reactants. So we're going to take the sum of the products minus the sum of the reactants. Alright, so if you take a look, the calcium chloride right here, if you go up to the top, the calcium chloride is going to have a delta H of negative 877.3. So we have negative 877.3 plus, we need to now do water, which is negative 241.82, plus carbon dioxide, which if you take a look up here, is going to be this one right here, which is negative 393.51. And right there, that's going to be the sum of the products. So again, we took the sum of the products, which is going to be right there. All right, the sum of the products. Okay, now what we're going to do is take the sum of the, we're going to subtract the sum of the reactants. So let's go ahead and do that. So we're going to subtract the sum of the reactants. And so the reactants are going to be calcium carbonate here. And so the calcium carbonate is right here. It's going to be negative 1207. So we're going to do negative 1207 plus hydrochloric acid. Now one thing I'll point out is hydrochloric acid has a coefficient of 2 here. So we need to multiply the heat of formation for hydrochloric acid by 2. So again, whatever the coefficient is, we multiply it by 2. And so hydrochloric acid is going to be negative 167.16. Put this in parentheses. And there's that. So let's go ahead and type that in the calculator. Take a moment to do that, and I will put the answer up in just a moment. Alright, so what I end up getting, it is going to be, yeah, so I did the math right here. It's going to be 28.69, and that is the answer that I get when I type that in the calculator. So what that means is that this will actually absorb energy when it is when it goes forward. So since we've got a positive 28.69, the next part we need to determine if it is endothermic or exothermic, and since it is positive, it is going to be endothermic. And for number 3, all we need to do is we need to take this right here, well, I don't know why that did there. So we need to take this right here, paste the reaction here, and we need to add this number, this amount of energy. By the way, this is going to be kilojoules. And so we need to add this energy to this over here. All right, so we need to add it to the reactant side because it's positive, so it's going to be 28.69. And that is going to be, oh, we need to add it there. And that is going to be the answer for number 3. So what I'm going to have you do now is do the practice problems on page 81. There is one more video to watch before the end of class, so make sure you use your time wisely. And again, next class period we will review this and do a review that is going to be for the test on Friday. So I do expect you to know this material.